Okay, everyone, welcome back to chapter 17. Now, in looking at the assignments that I've posted so far, in terms of chapters and labs, I think 17 is going to be the last chapter that we're going to cover. I originally had stated we'd go into chapter 18, but what I've done is taken some of the material from chapter 18, put it into one of the lab assignments. So I think we'll stop here, and then with sort of a final assignment, that'll get us to 25 assignments for the class, which I think is pretty good. So this will be the last chapter, and this is a pretty condensed chapter as well, so this probably won't be quite as long as some of the other chapters. What we want to look at here is we want to kind of dive back into thermodynamics and talk about how we can determine whether a process, whether that's a phase change or a reaction, is likely to happen, whether it's going to be spontaneous or whether it's not spontaneous under certain conditions. We saw a fair amount about thermodynamics back in the first semester of general chemistry when we talked about enthalpy. And enthalpy is part of kind of this overall decision as to whether a molecule, whether a process is going to be spontaneous or not. But there are a couple of other things that we need to factor in as well, and we need to kind of hone in on that first before we can decide whether a reaction is going to be spontaneous. The first one is a property called entropy, so symbolized by capital S. And just like enthalpy, we're always considering how the entropy changes with a process or a reaction. So this will almost always be delta S when we look at this. And entropy is a measure of how dispersed the energy is. It's often phrased as it's a measure of the disorder in a system, right? And that's a reasonable way to think about it. The second law of thermodynamics kind of relates to entropy. One of the ways to phrase that is that a spontaneous process is one that results in an increase in the entropy of the universe. So something that causes more disorder is likely to happen. The example I like here is maybe getting a little dated, but it's a good example as well. If you've ever had a pair of earbud headphones for an iPod or something like that, if you've ever taken your headphones and stuck them in your pocket, walked around for a while and then pulled them back out, right? They're almost always tangled up. So the tangled up version of the headphones is higher in disorder than the nice, neat, straightened out version. So just the process of walking around will tend to tangle your headphones up. Now, what you usually don't see is you take your tangled up headphones, you shove them in your pocket, you walk around, and it untangles them, because that would be the opposite of the direction of the second law of thermodynamics. That would be the system getting more ordered. And that is something that we generally don't see unless there's a consequent change in some other form of energy, which we will talk about when we get to seeing whether a reaction is spontaneous or not. We can overcome entropy if something else is happening in our system. Now, every particular material would have what's called a standard entropy value, again, kind of a measure of how dispersed is the energy. And we can make some comparisons here. So the first two entries here are both forms of carbon, the graphite version and the diamond version. And what we can see here is there's a little lower entropy for diamond than there is for graphite. This tells us diamond is a little bit more ordered in the way the carbon atoms are arranged. Graphite is a little more disordered. And if you think back to chapter 12, right, we said graphite is it's ordered in sheets. It's kind of a two-dimensional material with these weaker interactions between the sheets. So there's a lot more disorder there than there is in diamond, where every carbon is connected into a tetrahedral arrangement of the surrounding carbons. Now, if you change phase from solid to gas, there's a lot more disorder associated with the gas phase. So vapor phase carbon, the standard entropy value is significantly higher. It goes up to 158.1. So gases more disordered than liquids or solids. Liquids are generally going to be more disordered than solids, right? And that's something we'll have to factor into when we try to figure out what's the entropy change that goes along with a reaction. The other thing worth pointing out here is the units. So these are kind of the standard units for entropy. It's joules per k-mole. So one thing that we'll have to be very cognizant of as we go forward is that entropy is measured in joules, enthalpy and another quantity we'll see soon, free energy, are generally measured in kilojoules. So we'll have to take that conversion into account when those units are mixing together in a calculation. The other is the temperature dependence. Enthalpy, you may remember, is kilojoules per mole. So enthalpy is temperature independent. It doesn't matter what temperature it is, the entropy is the same. The enthalpy is the same one. Now, while entropy is also temperature independent, whether the effect entropy has on whether a reaction might be spontaneous or not is temperature dependent. So we'll see we're going to often end up multiplying the entropy value by temperature to get rid of that temperature dependence in the units so that we can start comparing it to the enthalpy. Now, down at the bottom here, we've got a calculation, and this is part A, there's part B on the next page. But we want to calculate the entropy change that goes along with a reaction like this. So in this case, we're just going from 1 mole of liquid ethanol to 1 mole of vapor phase or gaseous ethanol. Now, there's an equation that will allow us to compare the standard entropies for each material to the entropy for an overall phase change. And this will seem kind of familiar because there's a very similar equation for enthalpy that we talked about back in Chem 1. So the entropy change, in this case, right, it's not really a reaction in this case, it's a phase change, so just entropy change here, is going to be the sum of the standard entropies of the reactants minus the sum of the standard entropies. Sorry, I got that backwards. It's products minus reactants. Products minus reactants. Didn't sound right when I said it. I should have gone with my instinct in the first place. So sum of the let me slow down. Sum of the entropies of the products minus the sum of the entropies of the reactants. Now you can do the same thing with enthalpy. So the enthalpy for a reaction is the enthalpies of formation of the products minus the enthalpies of formation of the reactants. All these values are located in the back of the textbook. There's a big page in one of the appendixes back there, appendices, where you can find all this information. I've looked them up for these sample problems, so it'll look like I'm just plugging them in out of nowhere, but when you go to do some of the practice problems, you may have to refer to the back of the book to look up those values. So product is gas phase ethanol. So if I go to the back of the textbook, I can find that the standard entropy for gas phase ethanol is 282.6 joules per kmol. Right? And then I want to subtract the standard entropy of the reactant. So liquid phase, the reactant is a little bit more ordered, so it has a little bit less entropy. It's 160.7 joules per kmol for the liquid. So if I subtract here, I get the entropy change for this phase change is 121.9 joules per kmol. And that makes sense. If the disorder is increasing, like we would expect it to from a liquid to a gas, the entropy change should be positive. If the system was getting more ordered, we'd expect the entropy change to be negative. And in fact, entropy is kind of reversible the same way enthalpy is. If we did this backwards and we had the gas condensing into the liquid, right, these two numbers would change place. This would become a negative. So the reverse process would just have the negative entropy change.